this is the second part for the chapter 7 for MEC 551 air conditioning process. So in the previous section, we have looked on the fundamental aspect, the definition of the terminologies, for example, on the what is the specific humidity, what is the relative humidity, what is the dry bulb temperature, what is the wet bulb temperature, and then how to look on the psychrometric chart by the end of the slide presentation of the first part. So in the second part, we're going to do the analysis for the air conditioning processes that happen. So in brief, the definition, the analysis for the air conditioning process will involve the first thing is that you have to check whether the operating condition, okay, whether the operating condition is at the standard atmosphere or at not standard atmosphere. So why the first one is important? Because if it is at the standard atmosphere, 101.325 kilopascal, standard atmospheric pressure, so the psychrometric chart can be used, which is a simpler analysis or simpler processes of the formulation can be done. However, if the temperature or this pressure is not at the standard pressure, then you have to do the calculation for all the processes involved in order to determine the variables and the parameter involved in that processes. So the variables such as the specific humidity, relative humidity, the enthalpy, you have to calculate it when the not involved with the specific with the standard atmospheric pressure. But if it involved with the standard atmospheric pressure, you can just use the psychrometric chart to find the all the properties or the variables and as well the parameters. So if you imagine this is a simple psychrometric chart, what you have here. So this is a simple psychrometric chart. Okay. So this is a dry bulb temperature. So if we involve, we move from the left to the right. Okay. So this is the omega. This is the C. Okay. So this is a simple heating. Simple cooling. So left to right, simple cooling from this point to left. Okay. So this is a simple heating. This is a simple cooling. Humidifying process. So it will increase the specific humidity. So humidifying like that. So simple heating to the right, simple cooling to the left, dehumidifying go down. Okay. So if you imagine this is as the psychrometric chart, then you can understand how the processes will involve into the condition, the actual condition. Okay. So this is a simple one. Yeah. It depends on our desired temperature and as well the amount of the humidity level that we are looking. So yeah, so the various process of the air conditioning process, for example, the cooling move to the left, heating move to the right, humidifying move up, which is involving with the omega specific humidity, and move down for the humidifying. Then as well we have the combination of the heating and humidifying, cooling and dehumidifying. So we're going to analyze all the processes in here. Okay, so the simple cooling and simple heating. Let's say that we have a heating coil. Okay, so or maybe we have the condenser. Okay, in the more complicated processes. So let's say that we have a heating coil. Air enter at the temperature from the state 1 and exit at the state 2 with the temperature T1, omega 1 and Phi1. And then passing through the heating coil, the temperature will be increased. With the simple heating, we know that it is moving to the left. Why? The omega 1 is equal to omega 2. We're going to look after this. Why it is equal to constant? but the relative humidity will be reduced. Okay, we're going to look that as well. If we have the, or maybe from here. Okay. Okay, so, or if you have a simple cooling where the temperature at the higher temperature and then go to the lower temperature, passing before that it pass through a cooling coil or evaporator from state 1 to state 2. Okay, so simple heating and simple cooling. Firstly, we need to look on the, what we call that, the energy balance, sorry, the mass balance. Okay, so I'm there. Let's look on the mass balance. Okay, okay, so in here it have m dot a1, m dot a2, and then m dot v1, m dot v2. So for the mass balance, let's look on the dry air mass balance. Okay, so if we take the mass balance for the dry air, so what we have here is that m dot from the state 1, m dot a1, and then m dot a2. Okay, so which is also the summation of mass in equal to the summation of mass out. So which means that m dot a is equal to constant, right? So and then if we look on the if we take the water vapor, okay, m dot v1, the summation of mass in equal to the summation of mass out, which is m dot v1 equal to m dot v2. So m dot v1 is equal to m dot a omega 1, which is, we know that omega equal to m dot v over m dot a. Okay, so thus omega 1 m dot a 1 equal to omega 2 m dot a 2, but we know that m a1 is equal to m a2, so thus omega 1 is equal to omega 2. So with these conditions that we have here is that the specific humidity is constant for simple cooling and as well the simple heating. But if we look on the energy balance, okay, where summation of energy in equal to the summation of energy out. So what we have, m dot a1 h1 plus q in for heating depends on the operating m dot a h2. So with this condition, we can evaluate the amount of the q in is equal to mass flow rate ma h2 minus h1. Okay, all right. And this is a schematic diagram for heating with the dehumidification from state 1 to state 2. This is a simple heating where the amount of the heat is only put into the system, but between 2 and 3 there is a humidifier in between, so thus the amount of the moisture content will be different or will be increased. So if we look on the mass balance, if we do the mass balance, so what we have here for the water vapor, summation of mass V in equal to summation of mass V out between 2 to 3. Okay, So this is going to be m dot v2 or m dot, this is going to be constant, m dot a omega 2 equal to or plus moisture content m dot g, g representing of saturated vapor, equal to m dot a omega. Okay, I will do like this. This is a little bit few steps ahead. M dot v2 plus m dot g equal to m dot v3. So m dot v2 omega 2 ma plus m dot g equal to omega 3 ma. Okay, because the dry air is constant. Okay. Okay. So what we have here, the amount that, then the here the amount of the moisture that be added is equal to ma omega 3 minus omega 2, which is, if we look on the psychrometric chart, okay, we look psychrometric chart. Here, this is a state 1, move to state 2, and this is a state 3, where the specific humidity will be increased. So this is state 3. So from here, you can refer to the psychrometric chart to look on the processes, and as well on the value for the omega, the value for the enthalpy. Okay. But if you need to, but if this is not at the standard atmospheric pressure, then you have to do the calculations. Okay. So as for the energy balance, okay, so for the energy balance, I can take from 1 to 3. Okay, so m dot a, m dot a h1 plus q in plus in m dot g hg equal to m dot 3 m dot a h3. Okay, so yeah, so this is the energy balance from 1 to 3. Okay, so this is a cooling with dehumidification. Again, similarly, we can do the processes. For the mass flow rate for the dry air is constant. Okay, so the mass balance is only remaining for the water vapor. Okay, which is summation of mass in equal to summation of mass out. Okay, so it passing through a cooling coil until it achieve at the saturated vapor. So which means that saturated the phi has to be 100%. Okay, so which is, if we look on the psychrometric chart here, so the temperature cooling, state 1 cool, and then until state 2. So which is passing through here, it going through the saturated line, whereby here the amount of the omega will be dropped. So this is 1 until state 2. So the mass balance m dot v1, and then after that, here removal mf plus m dot v2. So amount of heat fluid rejected or condensed water rejected from the systems, m dot f equal to m dot a, which is mv1 equal to omega ma, so which is ma omega 2 omega 1 minus omega 2. Okay, as for the energy balance, summation of energy in, first law of thermodynamics, equal to summation of energy out. Okay, energy in, m dot a 1, m dot a, h1, normal in, out, equal to q dot out plus m dot f, hf, out, m dot a, h2. Okay, so m dot f is equal to here. You can put the equation there. So then you can solve the mathematical formulation for these conditions. Okay, so this is an example heating cross section. Okay, so you can do that at home later on. And this is for the cooling section, and this is for the heating section. This is for leave saturated part of moisture, condense, okay, remove. Then this is the cooling with dehumidifications. Okay, so this is your assignment. Due date is 15 June by 5 p.m. This is assignment number 2. Okay, so previous assignment for, okay, you can use with the psychrometric chart. This one you cannot use with the psychrometric chart. Okay, so in the synchronized class, we're going to discuss about these two problems. Okay, about the example, the previous example, to get you know how to use with the psychrometric chart, and as well on how to do the analysis to find the variables. So the next one is the evaporative cooling. This is the evaporative cooling is due to the swarm coolers, yeah, due to the nearby condition where it will be coolant with the amount of the water evaporations. Okay, so it will feel much cooler for the conditions. So hot air enter the evaporative cooler and then is sprayed with the liquid water. Part of the evaporate absorbing the heat from the airstream, and then airstream temperature will be decreased, humidity will be increased. And then the adiabatic, this is like, for example, if you like to watch with the you go to mama restaurant, and then at night where you have the live view for the football match, and then they turn on with the fan with the humidifier. So this is a similar processes that we have, where the humidifier is actually it is not humidified with the steam, but it is humidified with the mist. So the mist will take out the latent heat from the atmosphere and cool down the environment. So you will watch the EPL in the much better environment. Okay. Yeah. So this is the adiabatic mixing. If you look on those 4 processes before that we have, like for example, cooling, involving with the cooling coil or involved with the evaporator. Then you have with the heating, where it involved with the heater or condenser. So those 2 parts or 4 parts, which is actually involving with a lot of the electricity bills. So another innovative ways to reduce the amount of the power and or energy consumptions is to buy a mix, a flow that co-flow that has been processed and then come back together with the atmospheric air. So like this, for example, this is a treated air that you have. Okay, so let's say that this is a treated air, and then this treated air will be come back again, will be rejoined with the atmospheric air. Okay, so let's say that this treated air 25 degrees Celsius. Okay, and then come back join with the atmospheric air. Okay, so this is atmospheric air, 40 degrees Celsius. Okay, 25 plus 40, and then you also have the mass flow rate, and then the mass flow rate for the water vapor, mass flow rate for the one, and then mass flow rate for the water vapor, and also Phi1, and this is also Phi2. So we combine and then come up with the m dot A3, m dot B3. So with the new volume flow rate. So this is a mass dry air where you have m dot A1 coming, m dot A2, and then come up with the m dot A3. And the mass of the water vapor, omega 1 Ma1, omega 2 Ma2. So this is a water vapor that which is this one. Okay, and then come up with that one. And then you also can do the energy balance, which is this is also present H2, H1, and then come up with a H3. So from this, if we reduce the amount of the energy consumption, it can be redirected to our control environment, or in some cases it also can be treated with the evaporator, with the chiller, so that it can be reduced the amount of the energy consumptions. So for example, from here 40 degrees Celsius, 25, let's say it come up here 30 degrees Celsius. So 30 degrees Celsius to go down to 25 degrees Celsius, or to go down to 20 degrees Celsius, much lower energy consumption that can be used to reduce the temperature for air conditioning process. Okay, so this is the airstream from airstream 1 with the assumption where this is the process involved with the adiabatic. Okay, so how to come up with this one? So let's do the energy balance and the mass balance. Okay, so for the mass balance, okay, so mass balance for the water vapor. Okay, m dot, let's say m dot A1, m dot A1, m dot A omega 1 plus m dot A omega 2 equal to m dot A omega 3. Okay, so m dot A1, A1, A2, sorry, A3, so that's what we have. So dot A1, m dot A2, okay. Then what we have here, m dot, okay. Yeah, where m dot A3 equal to m dot A1 plus m dot A2. Then m dot A1 omega 1 plus m dot A2 omega 2 equal to m dot 1 A1 plus m dot A2 omega 3. Yeah, so that's one equation. Where if you rearrange this equation, what we have here is that m dot A omega 1, or yeah, m dot A omega 1, or you can yeah, like this for example. So you don't have to remember these equations. Yeah, so what we have here, m dot A2 omega 2 minus omega 3 equal to m dot A1 omega 1, sorry, omega 3 minus omega 1. Okay, so if you go down there and then here come down, so then m dot a1 over m dot a2 equal to omega 2 minus omega 3 over omega 3 minus omega 1. So you don't have to remember the equations. What you have to remember is that this mass balance and as well the energy balance. So omega 2, omega 3, so this is omega 2, this is omega 1, then omega 3 is in between. So this is the difference. Okay, then for the enthalpy change, so I will rubber this first. Okay, so let's do the energy balance. Okay, let's do the energy balance. All right, so for the energy balance, so energy balance, what we have here, m dot a h1 plus m dot a h2, so m dot a1 plus m dot a2 equal times with the h3. Okay, so you rearrange reorganize the equation. So what you have in the equation, m dot a h2 minus h3 equal to m dot a1 h3 minus h1. So you arrange the equation, then you will get this one. Okay, so thus the mass flow rate ratio will be depends on the difference of the ratio for the specific enthalpy and as well the specific humidity. Okay, so during the our synchronized class, we're going to look on this one as well. It's coming with your third assignment as well. Okay. Okay, finally we have a wet cooling tower. So wet cooling tower is not part of the air conditioning process, but the analysis is almost similar with the with the air conditioning process. For example, you have the energy balance here. Okay, this is in, this is out. Okay, this is out, this is in. Okay, so the warm water in, so m dot w1 air coming in, so you have m dot a1, and this is m dot a2. Okay, or if you have, this is state 1, this is state 2, state 3, and this is going to be state 4. So we have to do the mass balance and energy balance. So the power plant usually, this is the forced wet cooling tower, and as well we have the natural wet cooling tower, which is it has higher chimney, and then with the difference of pressure, it don't have a fan. Usually if you look in the power plant, I don't think that we have here in Malaysia. With this forced wet cooling tower, it contains a fan, and then it can absorb more of the air inlet, and then more warm water can come in, and then this warm water will be reduced, the temperature will be reduced, the warm air, the air inlet will reduce the warm water coming in, and then it will absorb and then drop down with the cool water in the below sections. Okay, the warm water, the warm air from the condenser pump to the top and straight to the airstream, the water droplet fall as cool water, and then this cold water will be collected and then will be bring into your AHU unit or into your chiller. Okay, so in the chiller environment where we have where we have the connecting with the chiller, I will draw it in the next sections, yeah, for our wet cooling system. Okay, so this is the a draft layout for the system, where you have a chiller or the refrigeration cycle, where this chiller or refrigeration cycle I will draw in red color, where you have a condenser. Okay, so this is a condenser. Okay, so usually this condenser is a heat exchanger. Okay, okay, so this one, and then before that you have a pump, and then before that you have a evaporator. So okay, I will redraw the evaporator and put in the yellow, blue color. Okay, because this is a colder conditions. Okay, so this is a cooler one. Okay, and then you have an expansion valve here. Okay, and then yeah, so this is the heating sections. Okay, so here, okay, so how does it connect with the wet cooling tower? So the wet cooling tower will be involved with here. Let's say that I put it here, warm is this is going to be a counterflow. Okay, so this is a wet cooling tower. So this is coming from the cool water. Okay, this is a cool water. So this is your wet cooling tower. Okay, cool water from the wet cooling tower. Then this is your fin before, and yeah, so before that, okay, coming in, and then after that this is going to be wrapped here, because this is a hot water, and then come, and then it's going to be spray here, and then here that you have a fan. Okay, so this is where the water droplet, this is air coming in. Okay, and here you have the, let's say, the cycle for the refrigerant. This is a cycle for the R134A. This is a wet cooling tower. Okay, so the wet cooling tower, the water, the cool water outlet be used into the heat exchanger for the condenser. Why the condenser need that? Because it requires higher capacity for the cooling process to take out the heat from the chiller. Okay, and how about the chiller? In here, the chiller, usually they will come with the okay, so this one, this is involving with the, this is involved with water plus glycol. Okay, and then this water glycol, then this one we go to AHU unit. Then this AHU unit will cool down. This is the water, this is a water cycle. Then this is AHU, and then the air will be ejected in here. So if I can redraw this one for the better view. Okay, okay, so yeah, this one. Okay, so let's say this is the AHU unit, go into the AHU unit, and then this is the air. Okay, so this is a cross flow heat exchanger, so there will be a lot of this, then come out and then go back into the cycle. So this is a water cycle. Okay, and then if it is involving with the cooling storage tank, for example in our engineering complex. Okay, so instead of this go to AHU, it go to the ice storage unit. Okay, so what happened in the ice storage unit? So at night, usually in order to reduce the energy consumption, because the electricity bill at night is cheaper than at the daylight. So what will happen there during the night after the office hour? The chiller will be operated to produce a lot of the ice, and this ice will be stored in the ice storage. Okay, so this is the ice storage. Okay, it will be stored here, and then when you're coming into the office in the morning, we go to the class, the ice the water we pump, and then we go to the AH unit without using the chiller. So it just use the ice storage here, which over the night the ice was produced by the chiller that use a smaller the same energy consumption but at the cheaper rate to produce a lot of the ice. So the ice is storage over the night. During the office hours in the morning, the ice will be used for the AHU unit here, and then after that you come back and then go into the cycle. Okay, and then reproduce and then come back for the ice storage again. Okay, or in some cases it will be bypass and go into your room. Okay, so this is the ideal one, but however the connecting, the piping system that we have in the engineering complex is not that good, because the ice storage location is quite far, which is at the near to the parking area. If you can see that it is located at the chemical engineering parking area, so it's quite distant, and then the piping system is not that good. After a few years, 10 to 15 years, that will be the flow is not that good because it's content of the glycol. From time to time it will leakage. It also have a reduce. It also have the what occur that the falling effect in the piping system. The friction increase, so it reduce the flow rate, and finally the maintenance has to be done. But however, it is not user friendly for the maintenance because the location for the piping system is not that designed well. So by the end, the ice storage is cannot be used. Okay, the system is good, but the handling operation is badly designed. That is why I say that, and that is what happened in the our engineering complex. And by the end, we cannot use this ice storage and then just fully depend on the chiller, which by the end our energy, the electricity bill is getting higher. Okay, so this is a wet cooling tower that use a natural draft wet cooling tower that use a high chimney that does not require with the external any power input. Okay, so this you can Google the natural draft cooling tower chimney. So this is another example. If we have time, then we're going to look on this one as well. Okay, so thank you very much. Please submit your assignment 1, 2, and 3 on time before 15th of June by 5 p.m. Okay, so I hope that thank you very much. You have gone through that. You will refer to this YouTube presentation frequently, and then we're going to have one synchronous class maybe on the today is 2nd. We're going to have it on the 3rd of June. Okay, so thank you very much.